Get going. Our quiz is Monday night. Where is our tentative schedule? There we go. So I got, I thought I had edited that. But maybe I did not. I sure did. I thought I had gone in and made some edits to the tentative schedule, overwritten the tentative schedule that was there before. One small but important change, and it's not there. Okay, I had gotten, let's get this over so I can make eye contact. There we go. I had gotten a little bit worried about putting 10.4 on the quiz because just about, well, everything that we would say about section 10.4, we would have to say tonight. And I would imagine you've already seen the 10.4 video and you know what's going on there, but it just, it felt a little bit uncomfortable putting 10.4 on there when really we haven't yet done section 10.3. I feel like I need to put 10.3 on there, so I don't feel quite so bad about that. But I think 99910, not really all that much. I would ask for a show of hands who wants hyperbola, ellipse, parabola problems on there, but I don't know that I will do that. 10.2 and 10.3. So omit 10.1, and that gives us at least 4 good sections to cover on the quiz if we leave off 10.4. So I do have a file somewhere on my computer that says quiz 7 will only be 9.9 through 10.3. So I will see if I can update that. So it will, that's what it will reflect. Hopefully we'll get to 10.4 and have a lot to say about 10.4 tonight, but because tonight is really, other than in the context of reviewing, it's the last time we'll really have a lot to say about anything. So I'd like to get to that. So 10.5 is really the only new material that has to be covered.
Hey, no!
Only the new material that has to be covered on Wednesday the 29th. So that's kind of where we are. Questions, comments, thoughts as we get going tonight?
Not that I can think of right now.
Nothing. Okay. Well, there's time for that. Let's look then. I believe I am sharing the screen that you see. Do you see example 5 right there on the shared screen?
Yep, we do.
Yes. Okay, good deal. So it says find parametric equations for this particular equation, familiar quadratic function, really, y is a function of x. Given a curve, which this defines a unique curve, there are as many as you want, different ways to put a parameterization on it. So here are just 2. One may be slightly more useful or interesting than the other, but they're 2 simple ones. Whenever you've got y as a function of x, one way that you can always parameterize it is simply to let t equal x. If you let t equal x, then immediately, of course, x equals t. That kind of goes without saying. You just need to express y in terms of t, but you've got that as well. Take the t and substitute it for x in the original equation, and you have y equals t squared minus 4. So just like that, you've got a particular parameterization. You could graph this on your graphing calculator in parametric equations mode. And let's see what that looks like. So we've got parametric equations mode. I am in polar mode, where I've been with my trigonometry class. And so y equals in parametric equations mode, there's a x equals and a y equals. So x simply equals t, and y is t squared minus 4. Of course, to display, get the calculator to display the t, simply press the xt theta n button and it will display the t. So t squared minus 4. Now, viewing window, we know what this graph looks like. It's a parabola, and its domain, the set of all x values in the equation y equals x squared minus 4, is negative infinity to positive infinity. So if we want exactly the same domain for our parametric equation, since x equals t, we'd want t to be negative infinity to positive infinity. So let me make note of that. T is between negative infinity and positive infinity. And as we graph it, of course, we can't input that into the calculator, but we could at least let t go far enough to the left and far enough to the right. So we're going to fill up the viewing window. And in fact, because the y value is so much greater than the x values here, that shouldn't be a problem. So I'm going to go maybe negative, I think we'll fill up the screen. If I go negative 5 to 5, that'll speed things up a little bit. Don't want to plot all that many points, so maybe the t step equals just 0.1. And the x min, let's go something close to the standard viewing window. Let's say negative 10 to 10. And it doesn't really have to be a square viewing window, so the y min also negative 10 to 10. Here we go. Look at the graph. And that's exactly what we would have expected to see. Now, what the feature on the calculator, if we're interested in what's going on for specific values of t, we could go second, and then on the calculate menu, we could do second calc value. And let's see, t equals 0 should be the point where x equals 0 and y is negative 4. So if we input t equals, I keep forgetting if got two screens and I didn't know which way to move the mouse to get to the one where I want it to be. T equals 0, x equals 0, y equals negative 4. That's the point. It just tells us where we are. If we trace from there, we can press the right arrow and it increases by the t step. So it increases by 0.1. So we can kind of see what's happening as t increases 1/10 of a unit at a time. Press it 10 times and we get to the point 1, negative 3, and we can keep going. Now we'll talk about derivatives of functions defined parametrically in the next section, but the calculator will do that for us now. If we want to know the slope of the tangent line, dy dx, we can input the particular value of t that we want. T equals, well, how about t equals 1 right there? I wonder what the slope of the tangent line would be at the point 1, negative 3. So there we go. And looks like 2 would be the slope of the tangent line. And certainly at the point 1, negative 3, that's where x equals 1. If we were to take the derivative of our function, which is 2x, dy dx equals 2x, substituting 1 for x certainly gives us 2 there. So various things we can do with the calculator with parametric equations. Now, the B part says, okay, go back to the same equation, same curve, but put a different parameter on it. Instead of letting the parameter be the x coordinate, which is really all we got in the previous one, let the parameter be the slope of the tangent line to the graph wherever you happen to be. So t equals m, the slope of the tangent line to the graph at the point x, y. So we just need to express that in terms of x. So let's see what that look like. M equals 2x, right? That would be the derivative of y with respect to x. M equals 2x. So with this particular parameter, x equals m over 2. Okay, so not a terribly difficult or stressful one, but maybe a more interesting one. X equals m over 2. Take that m over 2 expression, substitute it for x right there, and we'll have y equals m over 2 quantity squared minus 4. So the parameterization here is, let's see, x equals m over 2, y equals m squared over 4 minus 4, and then the value of m, basically, if x goes from negative infinity to positive infinity, that means m over 2 goes from negative infinity to positive infinity, so m itself goes from negative infinity to positive infinity. Let's see, if I leave t at going from -5 to 5, that would mean 2x in this case would go from -5 to 5. So x would just go from -2.5 to 2.5. We might need to go a little farther than that. I'm leaving it like it is, but we may see just an incomplete graph there. Give that a look. So y equals, for the moment, well, let's see, we got to change this. We can't enter an m, so I'm going to have to enter a t. So I'll enter t over 2. There we go. So if I could put an m over 2, I'd put m over 2, but t over 2 is what I put there. And for the other one, if I could put an m squared over 4 minus 4, I would, but I'll have to put t squared over 4. I overwrote. What happened? Minus 4. There. So look at the graph. The graph should have the same size and shape, and it might not be complete. I might have to go maybe m equals -10 to +10, but let's give this a look. Graph. There we go. So it's actually just going from x, it's m equals x, m equals 2x. It's just going, since m goes from -5 to 5, x only goes from -2.5 to 2.5. So if I want to see enough of the graph where it fills the vertical portion of the screen, I need to go farther to the left and right. So we can do that. Change the parameters so it goes -10 to +10 and grab it. There, so we see as much of the graph as we need to see in this case. Now, if we apply the parameter second calculate value, t equals 0, well, it's the same point as we got before when t equals 0. Before, what it meant was the x-coordinate at that point is 0. Now, what it means is the slope of the tangent line to the graph at that point is 0. Okay, and we could enter 1. There we go. If we enter t equals 1, that's a different point from what we had when t equals 1 a while ago. Before it was, I think, 1, -3. Now it's 0.5, -3.75. Before, when we entered t equals 1, it told us the point on the graph that had an x-coordinate of 1. Here, it tells us the point on the graph where the slope of the tangent line is 1. And I just think that's a little bit more interesting than the previous parameter. If I input 3.5, well, it's going to give us the point 1.75, comma, -0.9375. That'd be easy enough to find if we needed to, but we get directly that that's the point on the curve where the slope of the tangent line is 3.5. So a different parameter, kind of a different function, but a little bit more interesting than just kind of a basic parameter that we get automatically without having to think about it very hard. So as far as a quiz question, it's a little bit challenging to come up with a non-calculus parametric equations quiz question. I can think maybe given a parameterization, eliminate the parameter, and then just write it in terms of x and y. There was an example like that with an ellipse we looked at the end of class last time. Or something like this, I think, is maybe not that bad. Have a parameter that does a specific thing, like indicate the slope of the tangent line, or just give an equation with x's and y's and say, hey, give me a set of parametric equations that that gives us exactly the same curve as this equation with x's and y's. So that sort of thing. Gets a little bit more interesting when we start doing calculus with these, but 10.2 is a kind of a good review of parametric equations. On then to, let's see where we are, there was 10.3, and let's see if I can, there's 10.3. All right. Parametric equations and calculus. Let's look at the definition. You could take this as a definition, or perhaps even as a theorem. Ooh, if only we could read it. There it is. Okay, if we've got a smooth curve, something like that, and any point on there can be expressed where the x-coordinate is some function of t, and let's write it, let me make it clear that the x-coordinate is what we're thinking of as the x-coordinate. Maybe x of t, y of t is a little bit better way to say that, rather than f of t and g of t, so we don't lose sight of which one is which. X of t, y of t. The slope of the curve at any point xy is given by the expression below. So the slope of the curve, or the slope of the tangent line to the curve, is what is meant by this. In general, if we're exploring the slope of the tangent line, what we do is we kind of look at the particular point, and then we explore what happens when we consider another point. Well, I guess what happens when we consider another point close to that point, and look at the slope of that, we typically call it a secant line, the slope of that secant line, and as the x value, the difference between the x values approaches 0, then we look, well, what is the slope of the secant line approaching? Does that limit exist? And then we call that the slope of the tangent line. Well, in this case, what we do is we look at the ratio of the rate at which the y coordinate is changing to the rate at which the x coordinate is changing. Rather than looking at delta y over delta x, basically we look at dy dt over dx dt, and everything is happening as a function of t. So as we can, because we've got x expressed as a function of t and y expressed as a function of t in the parameterization, we are able to form the ratio of those expressions, and that's going to give us the rate at which y is changing with respect to x. So that's the ratio we will go with. If it's going to be well defined, so long as dx dt does not equal 0. When dx dt equals 0, we may run into a situation where we get a cusp, some point of non-differentiability, that sort of thing, or simply a place where the slope of the tangent line might be undefined. It goes vertical in places. So let's see how we might calculate dy dx for a given parameterization. Oh, I don't want to do example one. Example one in the notes, for whatever reason, I did a parameterization of the unit circle, but in an unconventional manner. I let the x coordinate be sine t and the y coordinate be cosine t, and it just ends up feeling all weird, because in unit circle trigonometry, the official definition of sine t is the y coordinate of that point, and the official definition of cosine t is the x coordinate of that point. Once we've got those definitions in mind, we can switch them back and forth if we want to, but it's really weird. And it has the if we look at the positive sense of the direction the curve is moving when t is increasing, it has it going clockwise rather than counterclockwise, starting at the top and going clockwise rather than starting at the positive x-axis and going counterclockwise. So it's kind of weird. So let's do this. Example, I'm going to call it 1.5. 1.5 for the curve parameterized by x equals cosine t, and way here, x equals cosine t and y equals sine t. That's the way we would expect it. Find dy dx when t equals, oh, what would we like t equal? How about 2 pi over 3? Over there in the second quadrant, 60 degrees off the negative x-axis, 2 pi over 3. So we have the x and we have the y. So we calculate dy dt equals, well, we're taking the derivative of sine t, that's cosine t, dx dt, we're taking the derivative of cosine t, that's negative sine t, and then we're finding the ratio dy dx equals dy dt over dx dt, that's cosine t over negative sine t, which is, it might be safe enough to leave it like that, or we could write it as negative cotangent. Okay, let's go negative cotangent. Negative cotangent of t. So, given any point then on the unit circle, okay, unit circle with the traditional parameterization where the x coordinate is cosine t and the y coordinate is sine t, the slope of the tangent line at the point where you have the point t, where the value of the parameter is t, it's going to be negative cosine t. So let's see what this does for us. The particular one we want is our unit circle. That one right there. So that's the point. The x coordinate is the cosine of 2 pi over 3, which is negative 1/2, and the y coordinate is the sine of 2 pi over 3, which is the square root of 3 over 2. That's the point where the action is happening. Dy dx equals negative cosine of 2 pi over 3. Well, let's see. That is, oh, wait, not cosine, cotangent. There. Negative cotangent of 2 pi over 3. So cotangent is negative in quadrant 2. Cotangent of 60 degrees, I believe, is the square root of 3 over 3. I believe the tangent of 60 degrees is the square root of 3. The cotangent of 60 degrees is square root of 3 over 3. So we want negative square root of 3 over 3. So what do you think? Does that look good? Would that pass? Would that line pass for one that has a slope of negative square root of 3 over 3? Maybe. Something like that. But that's the idea here. We can express, if we can express x in terms of t and y in terms of t, and it's a smooth curve, then we can express dy dx in terms of t by dividing dy dt by dx dt. The higher order derivatives, we can calculate the second or third derivative of y with respect to x using the parameterization. Just scroll down a little bit. Now, these formulas may seem a little bit weird at first because it seems like we're treating the y value differently from how we're treating the x value. The numerator kind of changes and we take higher order derivatives of the numerator, but the denominator seems to stay the same. It's just dx dt again and again and again. So I think it's good to just stop for a moment and think what we're doing when we're looking at the second derivative just of y with respect to x, and there's no parameterization in sight. When we look at just the first derivative, it's the rate at which the y coordinate is changing with respect to the x coordinate. So basically, if the y coordinate, well, what we do is this: we say, okay, how much is the x coordinate changing? So the x coordinate changes a little. The first derivative tells us the ratio of how much the y coordinate would be expected to change for a small change in x. Basically, take the change in y divided by the change in x, and that's what we're looking at for the first derivative. Second derivative is really asking the question: how fast is dy dx changing? How fast is the slope of the tangent line changing with respect to x? So basically, for a small change in x, what's the corresponding expected change in dy dx? So it's really the change in dy dx divided by the change in x. So in both cases, we're dividing by the change in x. That's what the second derivative tells us. Third derivative, we're wondering how fast is the second derivative with respect to x changing. So effectively, we're dividing a small change in the second derivative by a small change in x. In all three cases, we're comparing a change in some quantity, whether it's y, whether it's dy dx, or whether it's the d2y dx2. We're comparing that to a small change in x. If x increases by a little bit, how much are we going to expect? By how many times as much, I guess you could say, would we expect y to change, dy dx to change, or d2y dx2 to change? And so that's why, as we look at these, we're comparing dy dt to dx dt, and then we're comparing the derivative of dy dx to dx dt, and then we're comparing the second derivative of y with respect to x to the change in t. So here goes. We start off with dy dx equals dy dt divided by dx dt. There we go. Can't keep my the rest of my hand off the screen. It doesn't want to write when I touch the screen with my whole hand. Now, if I want the rate at which basically dy, the second derivative of y with respect to x is the derivative of the first derivative of y with respect to x, it would be what we want to do is look at the rate at which dy dx is changing with respect to t and divide that by the rate at which x is changing with respect to t. So ordinarily we would say, well, if dy dx changes a little bit and x is changing a little bit, correspondingly, what's that ratio? Here, we're comparing the rate at which dy dx is changing with respect to t to the rate at which x is changing with respect to t. We're comparing to the rate of change of t in both cases, and so this is going to give us that second derivative. Once we determine the second derivative of y with respect to x, we just continue this process for as many derivatives as we need. Now let's do one more. If I want the third derivative of y with respect to x, that's going to be the derivative of the second derivative of y with respect to x. So we want to compare the rate at which that second derivative of y with respect to x is changing to the rate at which, whoops, well, I was going to say ddt of just plain old x, but I can just say dx dt. There we go. So got one example where we go ahead and take 2 or 3 derivatives. In practice, I'm not likely to ask you more than just the first derivative, but I think it's interesting how we could calculate the derivatives, first, second, third derivative of a parameterized curve according to this formula, and then eliminate the parameter and calculate the derivatives the old-fashioned way if we've got y explicitly as a function of x, and compare and see how, hopefully, we get comparable answers using both methods. So here we go, and I'll go ahead and provide the picture. So given these parameterized curves, find dy dx, find the second derivative of y with respect to x, the third derivative of y with respect to x. Probably, since we're taking a bunch of derivatives, we'd want to write x of t as t to the 1/2 power rather than the square root of x. So, so that's what we'll do. And to get things started, dy dx equals dy dt divided by dx dt. Dy dt, we've got 1/4 t squared minus 1. So the derivative of that would be 1/2 t, I believe. 1/2 t. And for dx dt, if we call that x of t, t to the 1/2, that would be 1/2 t to the negative 1/2. So we should simplify that and go with dy dx equals, well, the 1/2s are going to divide out, and we'll get t to the 3/2. So there is dy dx. let's calculate another derivative. Now that we have dy dx in terms of t, we can. So d2y dx2 is going to be the rate at which dy dx is changing with respect to t. Whoops. The rate at which dy dx is changing with respect to t divided by the rate at which x is changing with respect to t. So if we take the derivative of t to the 3/2 and divide that by, let's see, dx dt we said was, do I want to leave that? I probably do want to leave that as a fractional exponent, 1/2 t to the negative 1/2. So what we'll have is calculate that derivative, 3/2 t to the 1/2 over 1/2 t to the negative 1/2. 3/2 divided by 1/2 is 3. And if we say t to the 1/2 divided by t to the negative 1/2, I'm thinking that's t to the 1. How do we feel about 3t there for the second derivative? Let's go one more derivative. The third derivative of y with respect to x is going to be the rate at which the second derivative of y with respect to x is changing, divided by the rate at which x is changing, both with respect to t. So that second derivative was 3t. So d dt of 3t, again, we're dividing by 1/2 t to the negative 1/2. Derivative of 3t with respect to t is 3. So 3 over 1/2 t to the negative 1/2. Simplifying, 3 divided by 1/2 is 6. So 6t to the 1/2. There we go. So in terms of t, we've got x, we've got y, we've got dy dx, second derivative of y with respect to x, and the third derivative of y with respect to x. Now, if we were to eliminate the parameter, we can express all of these in terms of just plain old x. So let's see. Eliminating the parameter, and x equals the square root of t, y equals 1/4. Got to solve for t in terms of x. Sometimes this is easy, sometimes it's difficult, sometimes it's impossible. In this case, I think it's maybe not too bad. If x is the square root of t, then x squared would be t. I believe we're only considering positive values of t, and that's fine. So we would substitute x squared for t here. And so y equals 1/4 x to the 4th minus 1. So to get this curve, and I think this curve goes all the way to the y-axis there, but to get that curve, we're only considering values of x that are greater than or equal to 0, because that have to be the square root of t, and that has to be the principal square root. But we can take derivatives of this. Dy dx equals, okay, 4 times 1/4 is 1, reduce the exponent by 1, and that's x cubed. How does dy dx equals x cubed compare to dy dx equals t to the 3/2 given the relationship between x and t? Is that what we would have expected there? T equals x squared. If we substituted x squared for t, I think we'd get a dy dx equals x cubed. Second derivative, just following the rules from Calc 1, d2y dx2 equals 3x squared. How does that compare with 3t? Well, if t equals x squared, it's right on. And finally, d3y dx3 equals 6x. How does that compare with 6t to the 1/2? Again, pretty favorably if x equals t to the 1/2, and it does. That's the correspondence there. So if we've got a curve that's defined parametrically and we have difficulty removing the parameter, but we've got x as a function of t and y as a function of t, we could come up with expressions for each of the derivatives of y with respect to x in terms of t, provided we can differentiate these expressions that are given. So kind of a useful fact there. So this is the would be a typical type of quiz question. Given a parameterized curve, find dy dx at a particular value of the parameter, whether it's t or m, whatever the parameter might be. All right, example 3. I think it's kind of an interesting example. Slope of the tangent line at the point where it crosses itself. In practice, it might be a little difficult to come up with the coordinates of the point where it actually crosses itself, as far as just an exercise of saying, well, where does it cross itself? How would we go about determining that? Let's take that point as a given. From the picture, it looks like the point 0, 2. Let's see if we can find the value of t that gives us the point 0, 2, and find, in fact, there are going to be two different, it looks like, values of t that do this. Find the slope of the tangent line at each of those values of t that puts the point 0, 2 on the curve. So if x equals, let's see, which one should we go with, sine or cosine? Probably easier to go with the y of t. Y of t y equals 2. So y of t equals 2. 2 minus pi cosine t equals 2. So negative pi cosine t equals 0. Well, for what values of t does cosine t equal 0? T equals pi over 2. And just looking at the x coordinate, I need the x coordinate to be 0. So t equals pi over 2. I think what we need are t equals pi over 2 and t equals negative pi over 2. I think these are the two values of t. These are clearly not the only values of t, because every odd multiple of pi over t makes cosine t equals 0. I have a suspicion these are the ones that we need, though. So let's try these and see what we get for the x coordinate. For the point 2, 0, of course, 0, 2. I've been calling that 2, 0. For the point 0, 2, we need the x coordinate to be 0. So what is x of pi over 2? It's 2 times pi over 2 minus pi times the sine of pi over 2. It's pi minus pi times 1. Sure enough, that's 0. So pi over 2 is one of the points, one of the t values that we need. What is x of negative pi over 2? That's 2 times negative pi over 2 minus pi times the sine of negative pi over 2. That's negative pi minus pi times negative 1, and that's also 0. So these are the ones, these are the values of the parameter that give us the point 0t. So let's find the derivative of y with respect to t and evaluate it at t equals negative pi over 2 and t equals pi over 2. I suspect, just based on the way the curve looks, that they're going to be opposites of each other. So I don't think these lines are perpendicular to each other, but I think the slopes are the same absolute value and opposite signs. That's what I'm thinking there. Okay, so dy dt equals, taking the derivative of 2 minus pi cosine t, so that would be pi sine t. I think so. Derivative of negative cosine t would be positive sine t. So the derivative of the 2 is 0. Dx dt would be 2 minus pi cosine t. So divide, or just write the ratio there. Dy dx equals pi sine t over 2 minus pi cosine t. So let's evaluate dy dx at two different values of t. Let's find dy dx when t equals negative pi over 2. That's pi times the sine of negative pi over 2 minus pi times the cosine of negative pi over 2. That's pi times negative 1 over 2 minus pi times 0. So this is negative pi over 2. How about that? Negative pi over 2. That's the slope, and it's a negative slope. So as we think about this, it's coming in, I believe, as t is increasing, the direction we're moving is that way, kind of in a sense, kind of for most of it from left to right. And so it goes, and t is probably negative values until we get to here. When we get to here the first time, t equals negative pi over 2. And so the slope of the tangent line would be negative, indicating if we were to increase, well, at that value of t, if x were to increase a little bit, y would increase by negative pi over 2 times that much. That's what we're saying. Now, t continues to increase. T goes from negative pi over 2. I'm thinking probably right here, t gets to 0. If we were to look at this, sure, yeah, the sine of 0 is 0. So the slope of the tangent line is 0 when t equals 0. And then t keeps increasing, and it comes around, and t is probably pi over 2 right there. So right there is what the slope we want when t equals pi over 2. So dy dt when t equals pi over 2 is pi times the sine of pi over 2 over 2 minus pi cosine pi over 2. So it's pi times 1 over 2 minus 0, which in this case is pi over 2. So the slope of that tangent line is positive. At that point, when x increases a little bit, y will increase by pi over 2 times as much. Y is increasing by pi over 2 times as much as x is increasing at that instant. So just kind of another example there, calculating the derivative, the slope of the tangent line given a parameterized curve. There are going to be 3 important formulas to be memorized, one here in section 10.3, and then 2 other important ones in section 10.5. We won't get to the 2 ones in section 10.5 tonight, but this one, it should be reminiscent of the formula for arc length that we saw in section 7.4. Recall in section 7.4, if we wanted to find the length of an arc, if y was a function of x, the length of that arc was the integral from a to b, where a and b were the x coordinates of points on that curve, of the square root of 1 plus dy dx squared, and integrate that with respect to x. Real challenge to find functions that you could take the derivative, square it, add 1, take the square root, and then still be able to integrate that. Hopefully it's not too much of a stretch in the absence of a direct proof here. I think it's reasonable to think if we were to parameterize this and input a substitute a dy dt and look at dy dx as dy dt over dx dt, we could carry out some algebra on this and come up with the expression that you see right there. So I spent a good bit of time with the oh goodness, with forming a partition of the interval and actually applying the mean value theorem, I believe came into play to come up with this formula. I'm not going to go there tonight, but just to observe that there is a striking similarity between this formula for arc length of a parametric curve and an arc length of a curve where we have y as a function of x. So basically, calculate dx dt, square it, calculate dy dt, square it, take the square root of the sum of those squares and integrate that between the t values. Now, we want to make sure that no segment of the curve is traced more than once, because if we're looking at a situation where we're going around a circle and from t equals 0 to 2 pi, we could apply this and no segment would be traced more than once. But if we went from 0 to 4 pi, what we should be getting is twice the length of the circle. But if it's traced more than once, we can't apply this formula directly. So we'd have to be careful to make sure we're applying this in the situation where no segment is traced more than once. I believe that's the case for example 4. So let's give this a look. The coordinates of a 4-cusped hypocycloid are given by this parameterization. X equals 4 cosine cubed t, y equals 4 sine cubed t, where t goes from 0 to 2 pi, and it's pictured there in the notes we saw in the corner of the screen a little bit ago. Find the total length of the curve. It's not difficult to see if we were just kind of trace around this thing that if we go from 0 to 2 pi, that no portion of this would be traced more than once. We'd get the entire curve, the 4 pieces of it, and that's all we would get. We wouldn't get any of it repeated. So if x equals 4 times cosine t quantity cubed, oh no. Yep, that means that means turn out the lights. The party's over. Gosh, I'd gone since the last time this happened to us. It happened again in a trig class. The pen just gave up the ghost. I've gone 3 or 4 consecutive class periods, and it's done really well. I think maybe it's user error, and I inadvertently, there's a little button on here, I inadvertently press that button, or just it thinks I'm about to press it, and after that happens, there's just no going back. So such a darn shame. Let's take a moment and look at the quiz that covered these sections up through 10.3, and let me see if I can give you an idea of what to expect on the quiz that you will see on Monday. So that'd probably be a good, if not better, use of our time than wherever I was going with that. So where am I going to find that? Oh, I've posted it, so I'm thinking, where are the old quizzes? Old quizzes. Quiz 7, I think quiz 7 in most cases went all the way through section 10.4, so I'll quickly look to the end and see if there's a problem at the end we can kind of eliminate. So quiz 7, we've got solutions for fall and solutions for spring. So let's look at spring, and let's go ahead and look at the one that has the solutions, because I'm not going to be able to write anything out. So I was making out some questions tonight, and I thought of a nice one that looks a whole lot like this one. This would be a good way. This is from section 9.8, and be a good way to get the quiz kicked off. Find a geometric power series centered at c equals blah. So pick a number, probably not 3, but some number to represent the following function. Probably not too big, single-digit number. Express the power series using sigma notation, indicate its interval of convergence. Okay, so maybe take a number other than 8, not that far from 8, but something like that. And in the denominator, we've got an x plus 1 here, change that up a little bit as well. So not difficult to come up with a nice enough problem with limited changes to what we see here. But it does bear some similarities to this. Basically, we want to take the expression 8 over x plus 1 and write it in the form a over 1 minus r. So the first thing that you see that I did there was I said, okay, I really need, because we want it centered at 3, I really need an x minus 3 down there. X minus 3 has to be a factor of the r. So I need an x minus 3, but it needs to have a minus in front of it, because I need something of the form a over 1 minus r. Now, sadly, the denominator, the x, has a positive coefficient. So if I'm going to be subtracting something with an x in it, that would give it a negative coefficient. So however it is I change it, it's got to be equivalent to the original expression. I've got to be able to simplify it and get that 8 over x plus 1 right back. So I write the x minus 1. I write that down. Sorry, x minus 3. I write that down. And then because I know I've got to be subtracting it, squeeze a negative 1 in front of the x minus 3. So I'll write, and at the moment, see, I don't know there's supposed to be a 4 there. I figure that out after the fact. That's the last part of this that I would write. So I think, okay, I write down at x minus 3. I put a minus 1 in front of it because I know my x has to have, I have to be subtracting it, but it has to be a positive coefficient. So double negative is what we need there. So if you've got the minus negative 1 times x minus 3, what would you have to add to that, or maybe subtract from that, to get x plus 1? Okay, so if you simplify the minus negative 1 times x minus 3, you just get x minus 3. So what do you add to x minus 3 to get x plus 1? You add 4. X minus 3 plus 4 gives you back the x plus 1. So you know, put a 4 there. So this expression, everything, it has everything that we need. It's got a number, and we're subtracting an expression that has a factor of x minus 3 that's going to be a factor of our common ratio. And if we simplify the thing, we get x plus 1. Now we still have the 8 up there. That's fine. The next thing we have to do is the 4 really needs to be a 1. 4 has to be a 1. How do we make that happen? Well, at this point, the only flexibility we really have is we can divide both the numerator and denominator by the same number. That's not going to mess with the fact that x minus 3 is still a factor of our common ratio. So divide both the numerator and denominator by 4. Divide 8 by 4 and you get 2. Divide 4 by 4 and you get 1, where we need a 1. And this expression with the x minus 3 in it also gets divided by 4. So it takes us here at this point. So we've got 2 over 1 minus this quantity, and it's exactly what we want. We've got the 2 is the a. We've got the 1 where we need to be a 1. We really don't have any options there. That has to be a 1 because we want it to fit this formula. And the r has a factor of x minus 3 in it. So this is going to be a power series centered at 3. And that's what we want. So there's a lot of pieces in the puzzle that kind of have to fit together. And it wouldn't be a bad idea for you just to practice this. Just pick random numbers from -9 to 9 and put them there, and maybe a number up in the numerator with a lot of nice factors like 8 or 12 or 24, 18, something like that, a really composite number. So when we divide, you don't get unsightly fractions. And just practice this and see if you can come up with this expression. So when you get to the quiz, whatever numbers I put there, you're going to be like, okay, I got this. So, so that's what you do. Well, we've got the first term, which is 2, and we've got the common ratio. So we've got a couple of options for the sigma notation. If you want k to start at 1, then you're looking at sigma k equals 1 to infinity of a times r to the k minus 1. And that's fine. That's the formula we use in pre-calculus, and we used most of our series started with k equals 1 early in chapter 9. Alternatively, you could let k start at 0, but then up here, instead of k minus 1, you would just have k. So not a huge difference there. Either one is fine. I'll look at it and I'll think, okay, does k start at the right place, and do you have the right exponent? Do they kind of match up and give you what you need? So either way is fine there. So there's the sigma notation. If we write out the first few terms, you can see the signs alternating there. What is the interval of convergence? Be sure and indicate. Did it say be sure? Yes, it did. Indicate its interval of convergence. Good news with geometric series. You don't have to check the endpoints, but you do have to take the common ratio and declare that it's between -1 and 1. Geometric series only converge if the common ratio is between -1 and 1. So solve that inequality. So x itself has to be between -1 and 7. So that's your interval of convergence from -1 to 7. The number in the middle is 3, and the distance to either endpoint is 4. So the radius of convergence is half the length of the interval of convergence, and that's 4. Is this a hard problem or an easy problem? From here to there. I think is probably the hardest part, coming up with that expression. Maybe one more step is difficult, but otherwise it shouldn't be terribly stressful. Not really taking any derivatives or integrals, so maybe it doesn't feel like calculus, but it's based on some important principles that are derived from calculus. So I think we can definitely pass this off as a calculus problem. Problem two there. Problem two. What I want to do is give you a couple of Maclaurin series. I don't want to have to ask you to memorize a bunch of these. There is a page of your textbook that has just a whole bunch of them, like a dozen different Maclaurin series. I don't know if I want to provide that, but I'll provide the ones that you need. In this case, sine x is provided, secant x is provided. And recall in class what we did last time was we took terms of a Maclaurin series on the left and multiplied by terms of a Maclaurin series on the right. And we got enough like terms where we can combine them and figure out, okay, what's the constant term of the product? What's the x term of the product? What's the x squared term, the x cubed term? Enough of these until we had the first 4 non-zero terms. So that's what I want to do, and I've got what I think is a fairly decent one. Give you 2 Maclaurin series, ask you to multiply them together and figure out the first 4 non-zero terms, and hopefully that won't be too terribly stressful. I don't ask you to divide one by another. That is kind of on the stressful side. It's tedious. I don't know if it's stressful. It'll probably be a really easy problem, but it's kind of tedious. How else do we come up with Maclaurin series? We take derivatives. This one, when I put it on the quiz back in that spring semester, what I was hoping students would realize is that secant x tangent x is the derivative of secant x. I don't think anybody noticed that. They just, maybe if someone handed me this problem, I might not have noticed that. It was by my design and I was thinking it, but that doesn't necessarily mean anybody else would pick up on that. So what I think they did was they went back. What did they do? I'm trying to think how students did this. They went back here. No? How would you come up with the Maclaurin series for tangent x? Maybe what they did was they just started taking derivatives and they used the definition of Maclaurin series to come up with terms of tangent x. That works for sure. It's a lot more work than what I was intending here. All I wanted students to do was say the derivative of 1 is 0. So no constant term. Derivative of, well, there could be a constant term had there been an x term to the one for secant squared, but there's not. Derivative of 1/2 x squared is x. Derivative of 5/24 x to the 4th is 5/6 cubed. That's all I was looking for on this problem. And some students got it right, but went all the way around the world to get there. So keep in mind that one way of coming up with Maclaurin series from existing Maclaurin series is to observe that the function that you're given has either a derivative or an antiderivative relationship to the function here. When we did at the end of class last time, there was a 1 over, let's see, 1 over 1 plus x and a natural log of 1 plus x. And the observation was that the natural log of 1 plus x was an antiderivative of 1 over 1 plus x. And we kind of needed to know that we could come up with a Maclaurin series for 1 and then be able to find an antiderivative of that term by term to come up with the Maclaurin series for another one. Once you do that, if you're not dealing with a geometric series, then you have to check the endpoints. So make sure to check the endpoints if it's not a geometric series for the interval of convergence. This problem 4 looks a whole lot like the one we just did a little while ago. So I think that would make for a nice quiz question there. X equals t squared minus 3t, y equals the square root of t. Find dy dx. It's just dy dt over dx dt and plug in for t. So that's a problem that typically goes well on the quiz. 5 is from section 10.4. And so that looks like it's not happening tonight. We've got officially a half hour left. I suppose it could happen tonight. It's just going to be difficult without a writing utensil. I can see that, but that's just four types of problems. I ought to be able to come up with more quiz questions than just 4. Oh, what am I leaving out here? Oh, something where just you've got a set of parametric equations. You want to eliminate the parameter. That's another good type of good quiz question, similar to what we did toward the beginning of class tonight. Let's see if there's anything different in the fall quiz. This looks like more of the same. Here are a couple of Maclaurin series, multiply them together and come up with Maclaurin series for the product. Oh, actually, another way of constructing Maclaurin series, the Maclaurin series for sine x is given here. The Maclaurin series for e to the x is given here, but wait, we don't want e to the x times sine of x. What we want is e to the 2x times the sine of 2x. So I guess there are 2 ways to go with this. What you could do is take these, sine x and e to the x, multiply them together, come up with a Maclaurin series for sine x e to the x, and then substitute 2x for x. That would then give you a Maclaurin series for e to the 2x sine of 2x. Alternatively, you could take the 2 Maclaurin series that are given, substitute 2x for x in each one, then you would have Maclaurin series for sine of 2x and e to the 2x, and then multiply them together. I think the latter way is probably a little bit more difficult than the former, but either way would get you there. So keep in mind that's another way you can form Maclaurin series by substituting 2x for x, x squared for x, that sort of thing. Problem 2, power series for sine x is given. Find the power series for cosine x. We did that in class last time. You just take the derivative and then more substitution. You can find the power series for cosine of 2x by substituting 2x for x. Let's see, this looks like, it looks like that hypocycloid we were gonna look at doesn't ask for the total length of it. What it does ask for, oh, that's in section 10.3, isn't it? The arc length formula. 10.3, where is 10.3? That's 10.2. Aha. Yeah, I don't know how that didn't make the quiz that spring, but that's a formula that really needs to be memorized for section 10.3 because that's where it shows up. So why do I not have a good quiz question like that? Oh, I'm lost now. That's probably the most recent one. There it is. So find the slope of the tangent line when t equals pi over 4, and that's like problems that we did. 4 is a section 10.5 problem. 5 is a section 10.5 problem. 6 find the slope of each tangent line to the graph at the pole. That's a 10.4 problem. Wait, this is a 10.4 problem as well. Yeah, so 5 and 6, and actually 4 are all 10.4 problems. So I guess a little good news. I'm limiting things a little bit, but bad news in that I don't seem to have a good example in a recent quiz of a problem that asks you to find the arc length, but I really need to put a problem like that on Monday's quiz because, well, we need enough problems on the quiz. So I'd give just 4 problems and at 25 points apiece, and that could be overwhelming. The arc length problem, it could be really easy. If you'll remember from section 7.4, when we did arc length and we did a surface area as well, for surface of revolution, it was just a matter of applying the formula and then coming up with a decimal approximation for the actual arc length using the calculator. So I don't think that's going to be a terribly challenging problem. It's just a matter of really memorization. So I think that's going to be certainly a reasonable thing. Let me just kind of stop here. I feel like it's a good stopping place. What specific questions you have about what we're looking at as far as Monday's quiz?
I don't really have any.
Okay, all right.
Not here.
So it seems clear enough then. Don't worry about section 10.4. I definitely watched the 10.4 video, and I would imagine we'll have some things to say 1 week from tonight on both 10.4 and 10.5. And between now and hopefully before that, I can start giving you a good idea of what to expect on the final exam. Typically, it's basically old quizzes plus new stuff. Problem from each of the old quizzes, likely plus a few problems from sections 10.4 and 10.5 is what you would be likely to expect on the quiz. As far as the proportion, I don't know, it feels like maybe 60-40, something like that, 60% old stuff, 40% new stuff. I want to be careful not to weight sections 10.4 and 10.5 too terribly heavily because we're seeing it just really quickly, kind of at the end of the semester, and it hasn't had time to assimilate. But maybe that's fresher on your mind than some of the stuff we did in chapter 7. So I'll try to think that through and put something in print as far as the types of problems to expect on the final exam. I feel like our time is going to be short when we meet on Wednesday, and there won't be time for me just to kind of wave my hands and say this is what to do. So I'll do my best to put something in print there. That's all I have. If there are no additional questions, thank you for being here tonight.
The only thing I got is I still didn't have the bonus points added to quiz 6. I don't know if you.
That's still not there. Is that the case for everybody? Bonus points for quiz 6.
I haven't checked.
Oh, it probably is the case for everybody. Thank you for mentioning that again. Evidently, I haven't added those. So I will look through. Well, I've got 22 minutes right now. That would probably be a good time. So I'll try to make good use of that time and see what I can do about that.
All right. Thank you much. Y'all have a good weekend.
Yeah, y'all have a good one. Yes.
I still have a little bit of. I'm a little bit confused about one, especially how it how it keeps repeating X. I'm sorry. I'm just a little bit confused about that. Why does it keep multiplying by X? Is it X to all the terms and then it's the next thing for sign to all the terms? Is that what's going on there?
Are we looking at
number 1?
Number 1 on quiz 7 solutions?
Yes.
Let's see. So as far as what is given information, so this much is given and this much is given. And then, so we're basically multiplying those two expressions together. And then your question is maybe what happens next? or after
So
that.
you just multiply x by everything on the right, and then the next one by everything on the right, and see what equals 0 and see what doesn't?
Basically so. When you multiply a polynomial, officially you're multiplying each term of one polynomial by every term of the other polynomial. So if you had the time, you could take and distribute that x across that entire polynomial. Now it has infinitely many terms, so you don't have that much time. So you just take it and distribute it across the terms that you need. So it turns out you really only need to distribute it across maybe the first 4 terms, because we get the first 4 non-zero terms by the time we get to the 5th power of x. And so multiplying x by each of those 4 terms is really enough to do that for you. Multiplying x cubed by the first 3 terms is probably enough. Multiplying x to the 5th by really the first term is enough. That's not exactly the way we set it up last time. And you kind of have to know how many terms you need from the beginning in order to do it that way. Last time, basically, what we did was we said, okay, we want to get an x term. How are the different ways that we could come up with an x term? And basically said, well, we can multiply an x term by a constant term. That's one way. We can multiply a constant term on the left by the x term on the right. That's another way, except there's no constant term on the left. So it's basically, you look at terms on the left and terms on the right and try to see how could you multiply those together and come up with an x term. How could you multiply terms on the left by terms on the right to come up with an x squared term? And if you consider all the different combinations of ways to do that, then you'll have enough terms to get the first 4 non-zero terms of the product.
All right.
Yeah. So I think I've got enough terms there.
What chapter is this again?
This was 9.10. It was the last section in chapter 9.
And what chapters are we primarily focusing on for the test, or the like major points?
They go back to 9.9, 9.9 power series, 9.10 Maclaurin series, special case of power series, and then 10.2, which are the parametric equations, and 10.3, where we find the slope of the tangent line for parametric equations, dx, and also arc length of curves that are defined parametrically.
All right, thank you.
You are welcome. Have a good one. All right, anything else, anybody? All right, I will go ahead and sign off then, and I will take a look at those bonus points in the few minutes that I have right now.